All right, we going to shift gears today and begin talking about electromagnetic radiation, and I'm going to talk about some areas and how they connect in this area dealing with light and electromagnetic radiation, and tie that into um, the electronic structure of an atom, basically the configuration of the electrons, how they are organized in a given element or atom. So we'll start out with a couple of definitions, and hopefully you grab this handout from Blackboard because I did upload it in the notes section. So we'll talk about spectroscopy. It's a really broad term, just dealing with the analysis of light emitted or absorbed by substances. There are lots of different areas of spectroscopy. There's infrared spectroscopy, UV spectroscopy, spectroscopy. So there are different areas of spectroscopy that actually take advantage of certain ranges of electromagnetic radiation. We're going to talk about that a little bit later. So every atom has its own unique spectrum, right? And every atom emits certain colors. And when it gets to, if you heat an element past a certain temperature, you get what's called the atomic emission spectrum. And that spectrum gives you, again, colors that are associated with that atom. So one, like a rudimentary basic spectrometer, you would bombard the sample with some type of energy. And in doing that, right, that sample gives off light, right? It gives off some type of electromagnetic radiation, which is picked up by a prism. And then after it's picked up by a prism, you can see that there basically is purple, yellow, and red that's given off from this particular element, right? So, and then that's recorded. And this is just a really rudimentary depiction of a spectrometer and how spectral lines for different atoms are recorded. So when we think about light, light is a very interesting topic because it's thought about as both waves and particles, which we're going to talk about shortly. So when we think about light, what is light? The most basic definition is that it's a form of electromagnetic radiation, right? So that's why you see this EMR, you'll hear the EMR spectrum, the electromagnetic radiation spectrum. That's all the different types of light that exist in the universe, visible and invisible. So when you think about light, when you see it, this is again thinking about something we talked about a while back, macro versus micro. These are microscopic properties that you cannot see, right? But all electromagnetic radiation has two components. It has an electric component and a magnetic component. So that's what the electromagnetic part comes in. So it has an electric field and a magnetic field. And this is all electromagnetic radiation. And so you can think about light in this sense right here. Let me go down to this slide right here, where you have the electric field vertically going up and down, and then the magnetic field going horizontally, the purple regions, right? And so when you think about the two fields working together, right, there's some definitions that we need to think about in terms of what these things mean as far as calculating the energy of light, calculating the type, determining the type of light that we're dealing with. And one of the things to think about is depicted here, the wavelength. That's this symbol, lambda. That's the wavelength of the light. And if you've taken physics already in high school, I'm sure you studied waves. The wavelength is just the distance between, if we have the peak here on this wave, well, on this point and this point on the wave, because you can see that the wave is oscillating. The wavelength is just the distance between those 2 points. All right. There's another component to this, which is that's connected to the wavelength, and that is the frequency. All right. So the wavelength is the distance between 2 points on a wave. The frequency is how often though that one of those points passes a specific point in time, right? And so that's why frequency is measured in hertz or 1/seconds. You'll also see this sometimes written as reciprocal seconds. But it's a cycle. How many times per second does this point pass a given point in time, right? Or given point in space. When you think about visible light, this is the frequency of visible light. So we're going to talk about visible light shortly. This is the spectrum that you probably learned in elementary school. The Roy G. Biv spectrum: red, orange, yellow, green, blue, indigo, and violet. The frequency of visible light is somewhere in the range of 5 times 10 to the 15 hertz. That's the range. Is the color of it is determined by the frequency. So whatever the frequency is, if it changes, then you also change the color that your eyes see. All right. So when we think about frequency with light, it is the number of times that point on the wave passes a point. And then the other part is the wavelength, which was discussed on this slide right here, right? It's the distance, and I'll highlight it again. You can see that wavelength. It's the distance between peaks, and is measured or described by the Greek lowercase l lambda, and it's measured in nanometers. So it's measured in nanometers. And remember, nano was one of our prefixes that we learned back in when we were looking at SI units and things like that. Nano is 10 to the minus 9 meters. So 1 nanometer is the same as 1 billionth of a meter. Sometimes you'll see the wavelength measured also in angstroms, but for the scope of this class, we're going to use nanometers or meters. So when we think about wavelength and frequency, the way that they go together is using this equation right here, which I'm going to show this a little bit differently. Right? So the speed of light, c, is a given number. That's a known number. 3 times 10 to the 8 meters per second, or 1.86 times 10 to the 5th miles per second. Now imagine that. Just put that in perspective in the sense of how many miles that is. That's 186,000 miles per second. Per second, not per hour, per second. And I told the morning class when we talked about this, there's a book called Range, and in that book, one of the things it talks about, is it Range? No, it's The Loop. There's a book called The Loop, I'm sorry, dealing with artificial intelligence. And one of the things it talks about is the race to get into outer space and go to another planet that's habitable. And the closest, what they call exoplanet to Earth, that's similar to Earth, with a similar atmosphere, so on and so forth, is about 4.1 light years away. Now, our best rockets travel at about 20,000 miles per hour. And to travel 4.1 light years, doing the maximum speed, which no rocket would ever be able to accomplish that without overheating or something. But to travel at that rate, it would take 131,000 years to get to that other planet. So just to put that in perspective, light travels 186,000 miles per second. And our fastest spacecraft travels at 20,000 miles per hour, right? So that's just to put that in perspective. And if we did the calculation, we could figure out how many more times faster light is than our fastest rocket. But the point is that light travels very fast. And so when we think about light and the speed of light and the wavelength and the frequency, this is how they're related, right? So light, the speed of light, c, right? And this is the frequency of whatever the light may be. It can be any kind of light. And this is the wavelength. So I can rearrange that equation to solve for either frequency or wavelength because the speed of light is known. If I have any of the other two, I can solve for either one. Right? It doesn't matter which one I have. If I have frequency, I can solve for wavelength. If I have wavelength, I can solve for frequency. We're going to talk about this a little bit later. Right? But when we think about the wavelength and we think about the frequency and the energy of light, all of that matters, and we're going to talk about how it's all related. But I want to make a point about the wavelength and the frequency here. So this is the spectrum I was telling you about. I just mentioned it earlier, the Roy G. Biv spectrum: red, orange, yellow, green, blue, indigo, and violet. What you'll notice is that energy is increasing in this direction. So energy is going up. Notice that the way you notice it, obviously, you have some energy values over here, and they're getting bigger. Right? This is the visible spectrum. These are all of the light. This is all the light that's visible to us. Immediately below the visible spectrum is the infrared spectrum. Right? So this is infrared. And notice the lowest energy light is red. So right underneath that is infrared. And then above it is the UV spectrum. So UV is here. And then let me make that. Infrared is here. And what I want to call to your attention is the relationship between the wavelength and the frequency. Light or energy, electromagnetic radiation that has longer wavelengths usually has also a lower frequency. So it's a lower energy radiation, right? Think about, I don't know, how many of you have ever done like the battle ropes when you're working out? I have some ropes in my garage actually. But let me put it in those terms. So if you're using the battle ropes, I know you've seen them before. If you want to really whip the ropes, you got to whip your arms fast, right? So you have to have a high frequency. And when you're doing that, you can see the wave going through the rope. The wave is going to be much shorter at a higher frequency. If you are just being lazy, taking your time, you can pick the rope up really high and then bring it down really slowly, and it'll be just one big loop, but the wave won't be as short. It'll be a big wave. And so that's the same thing with wavelength and frequency. You can look right here. The frequency of red light is 8,000. I'm sorry, the wavelength is 8,000 angstroms. Angstrom is also a unit of length, just like nanometers are. So 8,000 angstroms. And then the frequency is 3.7 times 10 to the 14 hertz. orange light, you can see the wavelength shortens quite a bit from 8,000 to 6,000 angstroms. And then by the same token, the energy goes up to 5 times 10 to the 14th hertz. I'm sorry, the frequency. The energy goes up to is 3.3. Here is 2.5. For yellow light, you see the wavelength shortens even shorter to 5750. And then the frequency goes up 5.2 times 10 to the 14th hertz. And then the energy also goes up, right? You can see that as well. So the relationship between the wavelength and frequency is that they're inversely proportional. Let me put all right, so what that means is that the frequency, let's just say the frequency is 1 over the wavelength. So high frequency low wavelength. We'll say low or short. Right? Short wavelength. By the same token, low frequency, long wavelength, right? So that's the relationship between them. And the reason I'm saying that is because there's a way to relate the frequency and the wavelength when you have to use it in an equation, which we're going to see in a second. So when we say the speed of light is nu times the wavelength, right? We can say that the speed of light divided by the wavelength is nu, right? If we wanted to solve for nu, which is the frequency. So this is an important relationship to keep in mind, because when we're looking at the energy of a photon and the energy of radiation, we're gonna use this relationship to substitute for the frequency, because sometimes you may not have the frequency of the light, but you may have the wavelength. And if you have the wavelength and you know the speed of light, you can always sub in this expression for that frequency. All right. Any questions so far? Anybody? All right. Let's go to the next part of this discussion. How did this get down here? All right, we're going to start talking about photons and quantum. All right. And I just thought about something. I was actually thinking about this morning when I was teaching this. If you ever notice on, like in the movies, lasers are always like red, and that makes no sense, because that's the lowest energy light, visible light that's there. And anything red beneath it is also lower in energy than that. You would think, now this is just me being a nerd, you would think that in a given movie, that a laser or something that's used, like, you know, like X-Men with Cyclops with his eyes, and the Red Witch and all these other characters, you would think that purple light would be the color of most of those devices and lasers and, you know, ray guns or whatever they use, but maybe they haven't thought about that. Anyway, that's just me being a nerd. All right. So let's talk about this, because in order to understand light and how to quantize it, how to determine the energy of a given light sample that comes from a given atom or a given element or a given source, we need to understand that light is basically thought of in two ways, right? And what we call the particle wave duality. So it's basically this little idea or concept. This concept basically says that light has both particle-like qualities and wave-like qualities. So we've seen the wave-like quality. That's why you can measure a wavelength or distance between the light waves or whatever. That's why you're able to measure that. We've seen that. But light also has particle-like qualities, which can be quantized. And so this concept is basically a merger of what we call classical mechanics and quantum mechanics. Classical mechanics is basically says that matter can have any amount of energy. It's limitless, how much energy matter can contain. But quantum mechanics, which is more well beyond the scope of this class, and it is a more of a PChem, like a physical chemistry and physics type of term, and a physics area of study. But it's basically the quantum part means that light or energy is quantizable, meaning that you can package it up in small packages and it can only be transferred in these discrete amounts, not unlimited amounts. All right. So when we think about a ray of light or a ray of electromagnetic radiation, because I think sometimes when we think light, we're just thinking about light that's in the room. But electromagnetic radiation can be infrared, it can be UV, it can be visible light, it can be gamma rays, it can be X-rays. So all these different types of EMR exist, and they all have specific energies and things like that. So we think about a ray of electromagnetic radiation. That ray can be a stream of what we call photons, right? And that's this term right here. So that ray can be made up of a stream of packets of energy that we call photons. So what a photon is it takes the particle characteristics of light into consideration. So a photon is like a particle of light. So it's a particle of light. And we can think about photons on a singular level, like a singular particle of light has a specific energy, but then we can also think about it on a molar level. Like if you have a mole of photons, you can calculate that energy as well. But right now we want to talk about the energy of a photon and how to calculate it. It's a very simple equation. It is H times nu, where nu is the frequency and H is Planck's constant. So that's Planck's constant, and then nu, we already seen that, is the frequency. All right, Planck's constant is a given. It's not a number that you'll ever have to calculate. It's a constant. So that means that has already been verified. You can look it up anywhere and it's going to be the same value, which is 6.63 times 10 to the minus 34th. Notice the units, joule seconds. Right? The joule seconds takes into account the fact that the frequency is in reciprocal seconds. So your energy is always going to be calculated in joules, right? So anytime we calculate the energy of a photon, it's going to be calculated in joules. So again, we mentioned this earlier with the different colors of light. The reason why you see that is because your eyes detect the different energies and those different energies have different effects on our eyes. So that's why red looks red and blue looks blue and green looks green and so on and so forth. And there's also, if we have some type of defect with our eyes, that's why sometimes some people can't see color. Sometimes people see only shades or different hues of a color, but not the actual color itself. So it just is, but it all depends on the energy of that particular light, red light, green light, blue light, so on and so forth. When we think about radiation, and the radiation that we experience on a regular basis, because we don't always experience X-rays. We definitely don't always experience gamma rays. which are very deadly. But UV radiation we experience every day because we go outside, the sun is shining. Even when the sun is not shining, UV radiation is still present. And so for UV radiation, the reason why the UV radiation is problematic and you want to limit your exposure to it, just like any other high energy radiation, is because you can break bonds with UV radiation. So I showed this example to the class this morning. And the reason why, again, UV radiation is dangerous is because you can actually break bonds. And that might not sound like much, but when you think about which bonds are getting broken, and you think about maybe cleaving off a functional group from protein, or cleaving off an atom and making a radical, then it becomes more problematic because radicals in the body are not good, right? They have to be scavenged. That's why that was a big push in the early 2010s and 2010, 2015, around that area, around that time span, to boost the amount of antioxidants that are in our diets, because antioxidants are known as radical scavengers. But if you take a molecule like ethane here and you treat it with UV light, right, you can actually break the hydrogen carbon bond, that covalent bond. You can cleave it and cut it in half, right? This is the organic part of me coming out. So, I like talking about this part here, right? So that's going to leave you with this. And a hydrogen radical. So these are what you call free radicals. But normally, especially in organic, you can actually take advantage of the fact that you can do chemistry like this with under UV light. And there's a whole, basically a whole sub area of organic that deals with doing radical chain reactions. As a matter of fact, there's an area of polymer chemistry where radical chain reactions are used to make polymers, right? We did a bonus assignment about polymers. I don't know, hopefully you remember, but a polymer is just a molecule that has multiple chains made up of monomers. And when you increase the number of chains in that polymer, you also change its physical properties. You might make it something that was a liquid and you polymerize it and it becomes like a solid or a foam, or it may turn into like a glass. Or if you take something like ethylene, which is a gas, and you polymerize it, it becomes like a plastic. So, but a lot of those processes are radical type processes where you generate a free radical and then it undergoes polymerization through some type of radical chain reaction. But this is why UV radiation is that's why you wear sunblock if you're going to be in the sun for a long time. And even for Black folks, yes, we have melanin in our skin, and it does help to shield the body from UV radiation to a certain extent, but it's still a good idea if you're going to be in the sun for a long period of time to wear some type of sunblock, because those UV rays can really do some damage to the chemicals in your skin. That's why sometimes you see people develop like spots. Sometimes people can develop skin cancer, all types of things because of excessive UV exposure. All right, so how does all this tie in? Well, before we do that, let's talk about how the energy of a photon, which we just showed a second ago, let's talk about that relationship between the wavelength again and the frequency, and how do we exploit that? Because every time I've shown you an equation, I've also shown you how to manipulate it to get what you want, right? So if the energy of a photon is Planck's constant times the frequency, and the speed of light equals the frequency times the wavelength. Then we can rearrange this and say C over lambda, which we just looked at a second ago, is the same as the wavelength. Then we can we can calculate the energy of a photon with either the wavelength or the frequency. We can say that E is H times nu, or we can say E is H times C over lambda. Right? Both of those will get you to the same conclusion, right? Both of those will get you the energy of that photon in joules. And remember, C is the speed of light, which is 3.0 times 10 to the 8th meters per second. Right? And then nu is the frequency, and lambda is wavelength. So you can have any of those two values and figure out what the energy of a particular photon is, because it's going to be associated with some type of electromagnetic radiation. It's not always going to be visible light. All right, let's see if we can, let's work an example, because this is not, this particular section right here is just manipulating the energy of a photon, and that's it, right? So let's take an example. Let's find out the energy of a photon that has a wavelength of 1700 nanometers. Right, 1700 nanometers. So let's figure that out. The way we would do that is to take our equation, E equals H nu, but we don't know nu because we don't have it, but we do have a wavelength. So we're going to take that expression H times C over lambda, and we're going to solve it. So E, remember H is Planck's constant, 6.63 times 10 to the minus 34 joule seconds. All right. And then the speed of light, we're going to just plug that in, 3.0 times 10 to the 8th meters per second. And this is over lambda, which is 1700 nanometers. All right, we got a problem right there. Because if you notice in the equation, we want to cancel everything. We want to cancel seconds, which we can do here. And we want to cancel meters, but we can't cancel meters with nanometers. So anytime you're working this particular type of problem where you're looking for the energy of a photon and you have the wavelength, you have to put it in meters. Well, if you remember from when we talked about units and unit conversions, a nanometer is 10 to the minus 9 meters. So we can just say this 1700 nanometers times 1 times 10 to the minus 9 meters over 1 nanometer. Right, so that'll cancel that. Now we can put this in scientific notation and say 1.7 times 10 to the minus 12, but we're just going to leave it. All right, so I'm going to take this expression here in nanometers, and I'm just going to change that. This times 10 to the minus 9 meters. All right, did everybody catch that? Everybody okay with that? So now I just need to plug this number in. And let's do that. Clear my calculator out. All right, so we're going to do 6.63. And if you have a little exponent key on your calculator, you can put that in to the negative 34 times 3.0 times 10 to the 8. And then we're going to just divide that by 1,700 times 10 to the minus 9 meters. Did anybody get the number? All right, so I got 1.17 times 10 to the minus 19 joules. And you can see right here, everything is canceling. So the meters are going to cancel. The seconds are going to cancel. And I'm left with my energy in joules. All right, so the energy of a photon that has a wavelength of 1,700 nanometers is 1.17, excuse me, times 10 to the minus 19 joules. All right. Now all that's good and nice and beautiful and all that stuff, but all that stuff is leading us to a point. And what we want to find out now is how this connects to atoms and their structure, because the way that atoms release electromagnetic radiation is telling about their structure. So when we see certain spectral lines for certain atoms, it's really telling about how the atom is organized as far as the shells where the electrons are. And so it brings us to this topic, or this definition, which is the photoelectric effect. All that is that is when you irradiate a metal surface with photons, right? Electromagnetic radiation could be any wavelength or frequency, it doesn't matter. What matters is that when the radiation that hits the metal surface, when it's at the right frequency, which is higher than the frequency of the metal, the vibration of the metal is already where it's already vibrating, because nothing is still. We talked about that. Anytime you have a group of atoms in an element, those atoms are always vibrating. They're never still. So when the frequencies match, then you can actually eject electrons from that metal, right? And when those electrons get ejected, that's how we define that as what we call a photoelectric effect. So when you think about the electrons that get ejected, let me say this. The ejection part happens in the valence shell. Right? When we talk about the valence shell, what we mean is the outermost shell, which we're going to talk about, because that also leads us to another point of discussion, which is, well, where are the electrons that are being ejected, right? We need to know how they're organized. And so every atom has what we call an electron configuration. And this is the what we call the Aufbau buildup that talks about the location of electrons, because every electron is in an orbital somewhere around the nucleus of the atom, right? So all electrons, because we've talked about this when we talked about atomic number and ions and things like that. So all electrons in any atom they live in what we call orbitals, right? And the orbitals are arranged in a certain way. And there are four types. You got four orbitals that exist. You have s orbitals, you have p orbitals, you have d orbitals, and then you have f orbitals. Right. So any electron that belongs to an atom is going to be in one of these types of orbitals. It's going to be in an s orbital, a p, a d, or an f. And if you look right here, you can see how the energy levels are arranged. And I showed this to the earlier class, and when I learned it here in a straight line like this. But this makes it much easier to think about, because you think about the energy. So the one right here is representative of the energy level. So you can see right here where it says increase in energy, right? So in the second energy level, you have two sets of orbitals. You got what they call subshells, 2s and 2p. In the third energy level, you got 3s, 3p, and 3d. Fourth energy level, 4s, 4p, 4d, and 4f. Fifth, 5s, 5p, 5d, and 5f. And then in the sixth, you go back to three subshells, s, p, and d. And then the seventh is S and P. Now I want you to notice the connection. So you don't spend your whole like summer trying to memorize this, right? Notice second energy level, seventh energy level, both have two subshells, S and P. The third and the fourth, I'm sorry, not the third and the fourth, the third, let me get a different pen. So the third and the sixth have three subshells, 3s, 3p, 3d, and then you have in the sixth, 6s, 6p, and 6d. And then in between the fourth and fifth, notice they have four subshells, 4s, 4p, 4d, 4f, and it's the same for 5. So if you remember that part, aside from the 1s, if you'll notice, the 2 and 7 have two subshells, the 3 and 6 have three subshells, and the 4 and 5 have four. That's an easier way to memorize the buildup. When I was an undergrad, I just learned it straight like this, across. You can do that, but sometimes it's about working smarter and not harder. And if you have a way to memorize it, and because it's going to fill up this way too, when you're building an electron configuration, you're going to fill up just like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, like that. So if you have a different way of remembering how the shells are organized, then it makes it easier when it's time to fill up the shells and make or write out the electron configuration. All right. So those numbers 1, 2, 3, 4, 5, 6, and 7. Those numbers are what we call, and we're going to talk about this on Friday. They're what we call quantum numbers. And then 1, 2, 3, 4, that's what we call the principal quantum number. It tells you what energy level you're working in. Right, so 1 is the lowest energy level, and then you go all the way to 7. Right, and in some depictions, like the one on the next page, right, it goes to 8. It just depends on what type of atom you're working with, because when you get into those lanthanides and those actinides, then those really get to be you have a lot of electrons, and you can fill up all of these orbitals, right, from 1s all the way down to 8s. All right, I want to talk about the orbital shapes, but I'm gonna stop and then we'll do that on Friday. We'll start with that. And then we're gonna do some examples of electron configurations and determining quantum numbers. And then we're gonna be done with this section. All right, and we'll talk about some periodic trends. And then the last thing that we're gonna talk about on Monday is Lewis structures. We're gonna learn how to draw Lewis structures. But first we gotta learn about valence electrons and all that stuff. All right. So we're going to stop right here and then we'll pick this back up on Friday.